Welcome to the Proton Guru video practice for topic 4.15. These problems will give you practice on radical halogenation of allylic and benzylic sites. Some brief and straightforward reading to help you get ready for these kinds of problems can be found in the Organic Chemistry 2 Primer 2019 by Professor Houjeiry and co-authors. You can find additional chemistry videos and information on how to match the videos up to the chapters in your course's textbook at protonguru.com. The first problem asks us to provide the possible reaction products for the given reaction and to identify what the major product would be. Usually in a lot of organic chemistry tests they will ask you for the major product, so that's an important thing to be able to pick out. First we have to ask ourselves, what type of reaction is this? And hopefully when you see NBS, you note this is N-bromosuccinimide, which has this particular structure, and this reagent is used to provide the bromine to replace a hydrogen. And the hydrogens that it can replace have to be at a benzylic site, meaning a carbon that's directly attached to a benzene ring, or an allylic site, which means at a carbon that is directly adjacent to the alkene carbon. And the net reaction is that the bromine replaces one of the hydrogens. Now this reaction involves radical intermediates, so when you identify the allylic and benzylic sites, which are the sites adjacent to an alkene, here we see two possible sites. And we have to think about what radical intermediates we could form at those sites before we proceed with the rest of the problem. Well, if I was to remove the hydrogen that used to be attached here, I leave one unpaired electron behind to leave a radical. And the same thing if I was to remove the hydrogen from that site. Now, one of the other reagents removes this. It's not actually floating around by itself, but this shows you that you're left with a radical at each of the two benzylic sites in this particular starting material. Now remember, if I have an electron that's not in a bond right next to a pi bond, I can also consider other resonance contributors. And we'll have to do that before we can figure out what all the possible products might be. So if I start out with a radical at this site, I can draw a resonance contributor where that electron and one from the pi bond adjacent pour into this space here, and I can have the other electron stay behind on this carbon. That's how I get this new pi bond here in this molecule, and I've moved the unpaired electron to this site. Likewise, with this initially formed allylic radical, I can put two electrons into this space, so I'll get a bond in the resultant resonance contributor. The second electron from that pi bond stays behind onto this carbon. So in all, I have four possible radical intermediates if I consider all the contributors to the structures. Now if I think about that, the NBS is a reagent that transfers a bromine to wherever I can make the radical, so the products that I would be able to get would be adding a bromine to that site, or to that site, or to that site, or to that site. And then if we consider those products, we see that we have these four potential products. Now here we're ignoring stereochemistry. Of course you've generated chiral centers in all the cases for this particular starting material, so they would all exist as racemic mixtures. But this question didn't ask us specifically about the stereochemistry, but it does ask us specifically about which the major product would be. As with many organic reactions, of course, the major product comes from the more stable intermediate. So we have one radical that has these two resonance contributors, and one radical that has these two resonance contributors. You say, well, which one of these is more stable? Well, they both have resonance, but in this case, both of the resonance contributors are secondary radicals. In this case, we have a tertiary contributor and a secondary contributor. So this is going to be the more stable of the two radical intermediates. But we still haven't finished out figuring out what the major product is, because we still have two potential sites where the bromine could add. There are two contributors to this intermediate. Well, the major product comes from the major contributor of this intermediate, which means the one that looks more stable, which would contribute more to the real structure. The tertiary radical is more stable, so the bromine that adds to that site will be the one that is the major product. So your major product looks like this. So just to recap the thought process, you figure out which are the allylic sites in the original starting material. You consider the additional resonance contributors that might be possible. You identify the more stable intermediate, it's the one that has the tertiary contributor, and then you add the bromine to the major contributor of the more stable intermediate, and you get this species, which of course has a chiral center right here, so you would expect a racemic mixture to finish out this problem. Here is a very similar problem asking you to provide the possible products and the major product for this particular reaction. And again, the first step is recognizing that when we see NBS, that is a reagent that can replace a benzylic or allylic hydrogen with a bromine. And here we have to identify the allylic or benzylic site. Well, since a benzene ring is involved, we say, okay, we're really looking for the benzylic sites, which is like this first example of the two possible choices for what NBS can do. Say, well, the benzylic sites would be the carbons directly attached to the benzene ring. It happens here that the molecule is symmetric, so it doesn't matter if I do a reaction at this or this carbon, they're both related by symmetry. And remember that for benzylic sites, the bromine will not add to the benzene ring. The radical resonance contributors would cause you to lose aromaticity if I was to move this double bond over in the course of doing a resonance structure, for example. So it's a lot easier in some respects than the allylic case. All we have to do is replace one of the hydrogens on the benzylic site with a bromine without considering all the different resonance contributors like we had to do with the allylic case. So we place the bromine there. Hopefully we recognize that we've created a chiral center, so this major product will exist as a racemic mixture. And not only is this the major product, it's the only possible product that doesn't cause you to lose the aromaticity, the great stability of this benzene ring.